Hey everybody, welcome to our third lesson. It's the first video lesson. The past lessons were, of course, those online simulations and such. But here we're going to have a video, and this one is going to be about reflection. To start it, I want to look at a little demonstration. I have here a piece of aluminum foil. I've kind of flattened it out so it's nice and it doesn't have too many crinkles on it. And what I'm going to do is I'm going to just kind of point it at my screen, and I want to look at what's on my screen by using this aluminum foil, the reflection of my screen. So I'm going to turn it right here. Actually, it looks a little clearer this way. Okay. So when we look at this, we can see there's this sort of rainbow pattern happening in the background. Now, that's not because of any sort of unique property of the aluminum foil. It's because, let me pull it up, this is the image that's currently displayed on my laptop screen. Okay, so what you're seeing is sort of a distorted version of that image. So one of the questions we're going to address today is, why is this distorted? If I held a mirror up here, you would see a very clear image of what's on my screen. But when we look at this, we just sort of see this rainbow blob, and so you're not able to see this image, but you can see sort of that similar pattern. All right, what I'm going to do next, and this is going to be the main topic that we're going to discuss today, is I'm going to take this foil and I'm going to crumple it up. So you watch. Okay, so take a look now. Do you see that rainbow pattern? Maybe a little bit, right? There's a little bit sticking out on some parts. Here, let me crumple it up even more. All right, so take a look now. Well, now when we look at this aluminum foil, we can barely see any of the rainbow. I think there's just maybe a touch right here. But throughout here, you don't see it at all. In fact, what you see is more white light, right? You see little dots of white reflecting off of this surface. You no longer see this clear rainbow. So the question that we're going to ask is, our aim, why does the reflection become white? And I just didn't want to write too much, but it's really, why does the reflection off of the aluminum foil become white after I crumple it up a number of times? All right, so let's jump into the lesson. Okay, so here we have that piece of aluminum foil from before, and just a reminder of what that aim was. Why does the reflection become white when I crinkle the paper up? So let's get into the lesson itself. To start, what I want to do is just very quickly discuss the reflection of a wave, right? We should recall that when a wave travels towards, this is a fixed boundary, the wave will interact with that boundary. The boundary, due to a Newton's third law, action-reaction pair, will cause the wave to flip over and then travel in the opposite direction. Now, what's key is when I have that aluminum foil and I bend it, or even before I bend it, what we're observing is the reflection of light from the aluminum foil. Now, light is, of course, a wave. We've established that. And so we expect it to demonstrate similar properties to a wave, such as the reflection of a wave. Now, towards the end of this lesson, we're going to talk about whether or not reflection itself is a property specifically of waves. So is the fact that light reflects proof that light is a wave? All right, so stick till the end and we'll discuss that. Now, to begin, the most common application of a reflection, that everybody I'm sure is familiar with is a mirror. Okay, so here I have somebody standing in front of this mirror, and they're going to be looking towards it like that. So if I wanted to draw their eye, it would look kind of like that right there, staring at the mirror. So when the person looks directly forwards like that, what they'll see is behind the mirror at some position, that same point. So they'll sort of like see their head back here. Right? Similarly, they'll see their body going down and their legs here and here, and their arms here and here. Right? That's what the reflection would look like. What's key to understanding what we as human beings see when we look in the mirror is knowing that our brain thinks light only travels straight. Okay, our brain thinks that the light will only end up traveling straight. But that's not true. Reflection says that that's not true. because reflection is the change in direction of the wave, in this case, the light wave. So then our brain, when it sees our foot over here, is actually seeing the foot over here, right? But because our brain thinks that it's coming from this position here, it thinks that the light is coming from, I want to draw this as well as I can, here. Okay. So when we look forward and we see our head, it's the light traveling towards our eye like that. Our brain thinks that the light came from here, but in fact it did not, right? It traveled to the right, reflected, and then traveled to the left. Well, when our brain sees the light come from here, it thinks that the light came from, let me continue this line, here. Right? It thinks it traveled in a straight line, which is why our brain processes that information and says, oh, my foot's over here. But in fact, there's no light behind the mirror, right? If a mirror is mounted to a wall, there can't really be much light behind it. There's certainly not another copy of you standing behind the mirror. And so that light must have come from somewhere else. Well, it must have come from the reflection of your foot here up to here. Right? So the light comes off of your foot to this point, reflects off of the mirror, and then reaches your eye over here, causing your eye to perceive and your brain to think that it came from this position over here. Right? So that's really how a mirror works. That's how the reflection of your image in the mirror itself works. Okay? Let's discuss now how we can explore what's going on at this position here. At the point where we switch mediums for a moment from the air into the glass and then onto the mirror, a mirror is really just a layer of glass with sort of a silvered background, which is what allows it to reflect, not unlike the aluminum foil from the demonstration. Okay, so we're looking at the law of reflection to explore how that mirror works, why the light reflects in the way that it does. So here I have this light ray that's coming from a point here. So like we can like say there's like a little dot here, an X on a wall or something. And so we see this, what we call the incident ray. Okay, incident ray is a way of saying the light that's coming towards the mirror. It will reach that mirror and it will reflect off of the mirror like this. Okay, this is what we'll call our reflected ray. Okay, that is the light that is reflected off of the mirror from this object. Not like unlike our foot, right? In the diagram that I had before, our foot sort of took a similar path, right? From foot, mirror, bounce off to the eye. That's exactly what we have happening here. Now, it comes in at some sort of an angle. So what I'm going to do is I'm going to draw a line here like that. Okay? This line is perpendicular to the surface. This angle right here, I'm going to label as theta I. And this one here, I'm going to label as theta R. Okay? This is my angle of incidence, and this is my angle of reflection. So again, angle of incidence, angle of reflection. All right, my two angles there. Really, really important is that these angles are always going to be measured from this dotted line here, that perpendicular dotted line, which is referred to as the normal line. It is the line perpendicular. Okay, so it is a line perpendicular to the surface of reflection. Right? We always measure with respect to the normal line. We do not measure with respect to the surface, okay? And the reason for that will become a little bit clearer in a moment. All right, let's look at a quick example. let's say here, I'm asked to find the angle of reflection of this problem. So I have the incident coming at an angle of 30 degrees with respect to the surface. Does that mean that theta I is equal to 30 degrees? No, right? Because this is not measured with respect to my normal line. This is not true. I need to find this here. Well, of course, that's a 90-degree angle. The normal by definition is 90 degrees. So this will be 90 minus 30, or 60 degrees. Okay, theta I is in fact equal to 60 degrees. Now, as I do this, I realized I wrote this down, law of reflection, but I never actually wrote the law of reflection down. Forgot to do that. Well, you should know from last week's activity, that online simulation, that the angle of incidence is equal to the angle of reflection. So this right here, this relationship, is in fact the law of reflection. Theta I equals theta R. I think I skipped it because it's kind of so obvious, but just know that that is the law of reflection. So here I know theta I. I can just apply the angle of incidence is equal to the angle of reflection. This will be reflected at 60 degrees. So this must be 60 degrees. Okay, so really simple problem, really just highlighting the fact that the angle is not found with respect to the surface, but with respect to the normal line, which is always perpendicular. That's the trickiest thing about the law of reflection. It's just remembering that you have to measure it from the normal. Don't forget that. All right, so now we're going to start to discuss the aim in a little more detail. There are two types of reflection we're going to talk about. The first one is what's called specular reflection. Now, when you think of specular reflection, I want you to think about a mirror. A mirror is a perfect example of specular reflection because when you look at a mirror, the image that is formed due to the reflection is nearly identical to the actual object, right? When you look at a mirror, it's not like you're all distorted. Your face doesn't look like a mess as if you're looking at this piece of aluminum foil. It's very clear what's going on. So if we want to be a little bit more technical with what it means to be specular reflection, we're talking about formation of an image when light reflects off of a flat surface. Okay, so when you have a formation of an image off of a flat surface, looking at sort of a diagram of what this would look like, imagine this is my flat surface, this is my mirror. Other things demonstrate specular reflection as well. A very still body of water, if you look in, you can actually see your reflection, right? That's an example of specular reflection. Suppose I have three rays of light that are running parallel to each other towards this surface, just like that. If I draw my normal line for each of these rays of light, again, perpendicular to the mirror or the surface of reflection, what we will find, knowing that we have three theta i's, right? And they all should in theory be the same. I know my diagram's not great. The law of reflection tells me that theta I equals theta R. So the reflected rays coming off should have that same angle. Just like that. Notice they come in parallel and they leave parallel. Because they come in parallel and leave parallel, due to the law of reflection, the image will be preserved. So if you look into a mirror, the light coming out will be all parallel. If I shine a flashlight, for example, this is a flashlight shining down this way, I'll see the flashlight bounce off this way. It'll still be clear. that beam of light that's being generated. That is specular reflection. Now, in contrast to specular reflection, we have what is called diffuse reflection. This is diffuse reflection. I have this bumpy surface with all these little crevices and dips and peaks on it. This is not nice and flat, and so therefore the image is not going to hit it and then bounce off in parallel. It's going to be scattered in all different directions. So I'll say when light is reflected off of a let's say a regular surface. Okay, now irregular is sort of a unclear word, but when I say that, I basically just mean a not a nice smooth surface. Okay, an example of a not very nice smooth surface could be like this. Right, so here I have a bumpy surface. I can draw my incident light rays again. Let's say I have this one. Let's say I have this one, and I have, this one. I'm trying to draw these parallel. I know they're not perfect. Well, now notice the surface is bumpy, which means that my normal line will be moving, right? The normal line is always perpendicular, so if this marker represents the normal line is constantly changing as I go. The law of reflection, theta I equals theta R, is still true. There's no reason why it would not follow the law of reflection. However, my normal line, the line that's perpendicular to the surface, is not always parallel to each other. And so the reflection, therefore, following the law of reflection, will do something like this. In fact, this is an interesting one because the first one's actually going to go here and bounce off the surface. Then I'll have another reflection here, a new normal line at that point of reflection, and it'll go off, still following the law of reflection like that. This one comes in, and it'll go off like that. This one comes in, and it'll go off like that. So now we see that this light is bouncing in all different directions. Now, it's still reflected, right? It's not as if the light disappears or is absorbed by the medium now. It's still reflected. It is still following this law of reflection. But it's what we call scattered. It's going in all different directions. And so if you are standing somewhere, you will not be able to discern the image that was originally reflected off of the surface, which is exactly the answer to the aim, right? When I had that nice flat piece of aluminum foil, we were able to partly make out the surface. That was not specular reflection because it wasn't a perfect image, but it was closer than this. This is not specular reflection because I have so many, it's clearly not specular reflection. Now, this white light that you see, the reason why it's turning white is because everything that was pointing at it is still reflected off, but it's not a clear image. Now my eye, your eye, when you look at the piece, is being bombarded with scattered light of all different colors. When your eye sees scattered light of all different colors, it says that's white light, right? And so therefore, even if I have a rainbow up here pointing down on it, you still see white because all of those colors are coming into your eye from all different directions and your brain can't sift through. If we were really, really clever and we got a perfect topography of this piece of aluminum foil and we studied all the light that's being reflected off of it, we could still recreate the image above it. But our brain is not able to do that because our brain says, if I see 3 colors coming from one point, I see white light. Okay? So there's the answer to the aim. Now, even something like this sheet of paper. This sheet of paper is white. This sheet of paper does not generate its own light, which means our image of it is just a reflection of the light around the paper. So when you look at this paper, what you're actually seeing is the light reflecting off of everything in the room that I'm in right now. Now, when I look around my room, I see all different colors. I see clear objects. So if this were a mirror, you would have specular reflection and you would just see a reflection of what's in my room. But because this paper is actually not smooth, it may seem like it is, but on the surface it's bumpy just like this is, just much smaller bumps. The light is diffusely reflecting off the paper, and so your eye says that's just white. But again, if you had a good detail of the topography of the paper, all the little bumps and crevices, and you studied the light reflected off, you would actually be able to recreate what's in my room right now. Okay, so that's it for reflection. I look forward to the next lesson.